Welcome. In this lecture, we are going to discuss about the basics of electronics. This is the outline for today's lecture. Okay, let's get into the course content. To start with, let's see what is electrical and what is electronics. Okay, simply we can state that electrical is the study of conductors and electronics is the study of semiconductors. So that is the simple statement. But in detail, we can state that electrical is a branch of science, okay, that deals with the study of flow and control of electrons and their behavior in conductors. Okay, so that is the detailed statement for electrical, and it can also be defined as the study of electricity generation, transmission, distribution, and then consumption of electrical energy at the user end. Okay, so these are the two detailed statements for electrical. And similarly for electronics, we can state that it is a branch of science that deals with the study of flow and control of electrons and their behavior in semiconductors. Okay, let's see about atoms and molecules. Atoms are the smallest indivisible particles of matter, which is named after the Greek word atomos. Atomos means that which can't be split. Okay, so since it is the smallest indivisible particle, everything around us is made up of atoms. So can we say like that? Everything around us is made up of atoms. Yes, we can say like that. And then an atom itself is made up of three tiny kinds of particles called protons, electrons, and neutrons. These protons, electrons, and neutrons are called subatomic particles. Okay, and then what is molecules? The group of atoms combine together to form molecules, or we can also state that molecules are the combination of atoms. Okay. Here, let's see about protons, electrons, and neutrons. So they are called as the subatomic particles, and they are also called as elementary particles, right? Okay. So what is protons? Protons are positively charged particles. Electrons are negatively charged particles. Neutrons are uncharged particles. So here the charges are common. So what do you mean by charge? So charge is nothing but the fundamental and characteristic property of the elementary particles. Okay, so these are the properties. So protons means it is having a positive property. Electrons means it is called as it is having a negative property, and neutrons is neutral property. Okay, and now let's look into the picture. Okay, so this is a atomic structure. Okay, so in the atom we know that we are having protons, electrons, and then neutrons. So here you see the protons and the neutrons. Okay, just yeah, you see the protons and where is here is the proton. Protons and the neutrons are joined together, and this forms the nucleus. And this is what this is the nucleus. And you see the negatively charged particle, that is the electrons, are orbiting. Orbiting means revolving around in a concentric path. Okay, so the electrons are revolving around the nucleus. So this is the atomic structure, and this is the Bohr's model of atomic structure, right? Right. Let's see some important terms and definitions. So the first one is, what is a shell? So the electrons which orbit the nucleus in a concentric path is called shell. So we can state like that. Consider this as a nucleus. Okay, this is a nucleus, and if the electrons revolve around in a concentric path, then it is called shell. Okay, and an atom can have one or more shells. All right. Okay. So that is called a shell. And the second one is the maximum number of electrons that can exist in each shell of an atom can be calculated by the formula Ne is equal to 2 times n to the power 2. Okay. So this Ne is the maximum number of electrons in each shell, and this n describes the shell number. Okay, so n describes the shell number. N describes the shell number, and Ne is the maximum number of electrons in a shell. Maximum number of electrons in a shell. All right, in a shell. So that can be, so the maximum number of electrons in a shell can be calculated using this formula. All right. And if you see this picture, this is nucleus and this is shell number 1 and this is shell number 2. Right. And then what is valence shell? The outermost shell is called valence shell. So in this picture, this is the outermost shell, and that is called as the valence shell. Okay, so this is the valence shell. Valence shell. All right. And what is valence electrons? The electrons in the outermost shell is called valence electrons. So this is the outermost shell, and if there are some electrons here, then that electrons are called as valence electrons. Okay. And the last term we need to identify, or last definition, is that when a valence electron gains sufficient energy from an external source, it can break free from its atom. Okay, this is the basis for conduction of materials. Yes, so when an electron gains energy, it can be heat energy, it can be light energy. So you see the electrons in the valence cell, when it gains heat or light or any kind of energy, when it gains some energy, it can come out of this atom and it becomes a free electron. And you know the free electron is the basis for the conduction of materials. Okay, let's answer some of the questions here. So the first question is, how many shells are there in the silicon atom? So here there are two pictures, and the first picture is a structure of silicon atom, and the second picture is the structure of germanium atom. All right. So here the first question is, how many shells are there in silicon atom? So this question, for this question, we have to look this silicon atom, and then we should know what do you mean by shell. So we know that shell is defined as a concentric path. Cell is defined as a concentric path in which the atom revolves around the nucleus. So that is the definition of cell. So how many shells? So here we can say that this is shell number 1, because there are some electrons which revolve around the nucleus in a concentric path. So this is cell number 1, and here there is some more electrons which revolve around the nucleus at certain distance in a concentric path. So this is cell number 2 and this is shell number 3. So when it comes to silicon, the number of shells is what? 3. Okay. Okay, all right. Then let's move to the second question. What is the maximum number of electrons that can exist in valence shell of the silicon? So valence shell. So this is also with respect to silicon atom. So the valence shell, what is this? Valence shell is, this is the valence shell. Okay. The third cell is the valence shell. So we have to find the maximum number of electrons. So if you want to find the maximum number of electrons, then we know the formula n is equal to 2 times n to the power 2. Okay, so So 2 is there multiplied by this n is a valence shell. So this is the shell number. So in silicon, the valence shell is 1, 2, 3. Third shell is the valence shell, and we can write 3 to the power 2. Okay. So this is in case of silicon. So it will become 3 times 3 is what? 9. So the maximum number of electrons that can exist in valence shell of silicon is what? 18. So 18 is the maximum number of shell. Alright. Okay, then let's move to the third question. How many electrons are there in the valence shell of silicon and germanium atom? So here we have to look both the atomic structure, silicon as well as germanium. And the question is, how many electrons are there in the valence shell? So here in silicon, the valence shell is this one. Okay. And for germanium, the valence shell is this one. That is, this is first shell, this is second shell, this is third, and this is fourth shell. So fourth shell is the valence shell for germanium atom. Third shell is the valence shell of silicon atom. But the question is, we have to write how many electrons. So let's look at this silicon. So for silicon, the valence, so the number of electrons is, this is 1, this is 2, this is 3, this is 4. Therefore, for silicon, the number of electrons in the valence shell is 4. Then let's come to germanium. So it is 1, it is 2, 3, 4. So there are 4 electrons in the valence shell. Therefore, for germanium also, the number of electrons in the valence shell is 4. So the answer is 4, right? And the last question is, what is the maximum number of electrons that can exist in the valence shell of germanium? All right. So here we have to do the calculation here. So the valence shell of germanium. So let's do the calculation. Ne is equal to 2 times n to the power 2. So in case of germanium, the valence shell is what? 1, 2, 3, 4. So fourth cell is the valence cell. So we have to write 4 and to the power 2. Then that is equal to 2 times 4 into 4 is what? 16. Okay, so 2 times 16 is 32. So the answer is what? So 32 electrons can exist in the valence shell of germanium. All right. Okay. All right. Now let's see about the categories of materials. All right. So in terms of the electrical properties, materials can be classified into 3 groups. One is the conductor, and the second one is insulator, and the third one is semiconductors. So in general, we can say that conductors are the one which easily conducts electricity. Example, copper, silver, gold, aluminum, and so on. And then insulators are the material that doesn't conduct electricity. For example, we can say that rubber, plastic, glass, mica. And semiconductors are the material whose conductivity lies between conductor and insulator. Okay. Or the ability to conduct electricity lies between conductor and insulator. Example, silicon, germanium, gallium arsenide, and gallium nitride. Okay, so in general, we can state like that. But in order to define in a specific way, you can use the word conductivity. Okay, conductivity and conductivity and resistivity, right? So with these two terms, you can define technically. For example, in conductors, we can state that the conductivity is maximum, okay, and the resistivity is minimum. So with these two technical words, you can define more technically. All right. Then when you come to insulators, you can define that the conductivity of the insulator is minimum, okay, and the resistivity of the insulator is maximum. All right, then when you come to semiconductors, you can state that the conductivity as well as the resistivity lies between the conductors and insulators. Okay, so it ranges. Okay, it ranges. There is a range that you can define semiconductors. All right. Yeah, we can also define using the energy diagram. Okay, so here you can see for conductors, the conduction band and the valence band are overlapped. Okay, so there is no band gap. So when it comes to conductors, there is no band gap. Okay, all right, right. So then when it comes to semiconductor, there is a small band gap between the valence band and conduction band. So the band gap is small. All right. So when we discuss about insulator, the band gap is very high. Okay, the band gap between conduction band and valence band is high. Okay, so that is why here, since it is overlapped, you can easily have free electrons. Okay, so in conductors, the free electrons are there. Okay, but in case of semiconductors, you need to give some external energy so that the free electrons may come out and then it can conduct. But in case of insulator, it is very difficult uh, to get free energy. Okay, so you have to spend a lot of energy to bring the free electron out, which is a little bit difficult. All right, let's see some important terms and definitions with respect to the energy diagram. So with respect to energy diagram, we should know what is valence band, what is conduction band, and what is band gap or energy gap. All right. So let's see what is valence band. Okay. So the valence shell of an atom represents a band of energy levels. All right. So let's assume that this is a nucleus. Okay. And these are shells. One, two. Okay, so for example, this atom is having two shells. This is number one, this is number two. Okay, so if it's a two shell atom, all right. So the valence shell of an atom represents a band of energy levels. Okay, you see the two is the valence shell and it represents some energy level, and the valence electrons, and it may also have some electrons, it can also have some electrons, and that are confined to that band called valence band. Okay, so that electrons are confined to that band called valence band. So that is called as valence band. So that means after this valence band there is no shell or there is no electron. All right. Okay, and let's look into the conduction band. All right. When an electron gets additional energy, it can leave the valence shell and become a free electron. All right. So this one we can state like that. So there are some electrons here, but when an electron gets additional energy, so when it gets an additional energy, this electron will come out of that band. Okay, and it come out of the shell. So now the nucleus doesn't have any control over the electron, and that electron will be the free electron. Okay, and that free electron is can exist in a band. It will be having a place to sit. So that place or that band is called as conduction band. Okay, so that means when it gains an energy, it comes out and then it exists in a band, and that band is called as conduction band. Okay, right. Then let's move to the next definition, that is band gap or energy gap. Okay, so the difference in energy between the valence band and conduction band is called as energy gap. Yes, so you see, this is valence band. Okay, that means the valence shell is the valence band. We can say like that. The band means it's a group of shells is called as band. We can say like that. All right, so this is the valence band, and you see the electrons gain energy and it escape from this shell and it exists in a band called what? Conduction band. So let's assume that this is conduction band. Okay, so there is a gap between between the valence band and the conduction band, and this band is called as what? Band gap. Okay, so that is why in the previous slide we were discussing like this. Okay, so one is valence band and another one is conduction band, and this is what? Band gap. And the band gap is very small, so that there may be a free electrons, and this is applicable for conductors. Okay, and if the band gap is very small, then it is for semiconductors. If there is no band gap, if it overlaps, then it is for conductors. Okay, but the band gap is very high for insulators. All right. Okay, and let's see the types of semiconductor. So as we know that semiconductor is a material whose conductivity lies between conductor and insulator. Okay, so some of the example, but the semiconductors are classified into two. One is extrinsic and another one is intrinsic. And the extrinsic semiconductor are further classified into two types, that is p-type semiconductor and n-type semiconductor. So here you can note something, right? So what is n is equal to p? N is the number of n is the number of electrons, p is the number of protons. So when the number of electrons and number of protons are equal, then it is called as intrinsic semiconductor. Okay, but when the number of electrons and the number of protons are not equal, then it is called as extrinsic semiconductor. Okay, so that is the broad classification. But when you come to extrinsic semiconductor, the number of electrons and the number of protons are not equal. So there are two more possibility. Either there can be more number of electrons or there can be more number of protons. So so it is again divided into two. Okay. So for example here, when the number of protons is greater than number of electrons, then it is called as p-type semiconductor. And when the number of electrons is greater than number of protons, then it is called as n-type semiconductor. Right. So here the intrinsic semiconductor can also be called as pure semiconductor, and the extrinsic semiconductor can also be called as impure semiconductor. And we know that for intrinsic semiconductor, the number of electrons and holes are equal. Okay. And for extrinsic semiconductor, the number of electrons and holes are not equal. So the number of electrons is not equal to the number of protons or the holes. Okay. So this one normally we have to add some trivalent or pentavalent impurities. Okay. To form the extrinsic semiconductor. That is why it is called as impure. For example, silicon is there. So silicon is a semiconductor atom. So you have to add any pentavalent or trivalent atom. Like you see arsenic, antimony, phosphorus. They are pentavalent atoms whose valence electron is 5. Silicon is having the valence electron as 4. So if you add 5, okay, if you add 5, for example, arsenic is also a semiconductor, and this becomes, it is having 5 valence electrons. So if you add these two, then the number of electrons and number of protons may not be equal, and uh, it will become an impure semiconductor or extrinsic semiconductor. All right. Similarly, when you add silicon plus boron, okay, so silicon is having 4 valence electrons and boron is having 3 valence electrons. So again, both of them are not similar, and because of that we can say it is an extrinsic semiconductor. All right. Okay, this is the structure of intrinsic semiconductor. So here this is a silicon atom. Okay, so here you can see silicon atom. There are 4 protons here and then 4 electrons which is shared with the neighboring silicon atom. So for instance, you can look into this one. So this is silicon atom is having 1, 2, 3, 4, is having 4 valence electrons, and it is surrounded by another 4 silicon atom, and each silicon atom shares 1 to this silicon atom. Okay, 1 to this silicon atom. Okay, so now you can see for this silicon it is having 4 valence electron and each silicon atom shares 1, so making it 4. Okay, so now the number of electrons in the valence band is equal. Okay, and there is no extra electron or there is no extra proton. Okay, and this is called a pure semiconductor. You see, all the atoms are silicon. Okay, therefore it is called as intrinsic semiconductor. But here you can see that here there are 4 silicon atoms, 1, 2, 3, 4, and this atom is antimony. Okay, this atom is antimony, and this atom is having an extra electron because this is pentavalent. This is pentavalent. Antimony is pentavalent. That means it is having 5 valence electrons. Okay, it is having 5 valence electrons. So that extra electrons is a free electron. Okay, it can share 1 electron each to this silicon atom. Okay, 1 to this silicon atom, and 1 to this silicon atom, and 1 to this silicon atom, and 1 to this silicon atom. But what about the 5th electron for the antimony? It is free, and it can come out and it can conduct electricity. We can use this electron to conduct electricity. And here you can see that there are 4 silicon atoms and 1 antimony, and therefore it is called as extrinsic semiconductor. Okay, and you can see this is boron. This is also extrinsic semiconductor. Boron is having 3 valence electrons. Okay, 3 valence electrons. All right, so here you can see that boron can share 1 with this silicon, and it can share the another 1 electron with this silicon, okay, 1 with this silicon atom and another 1 with this silicon atom, and it can share the 3rd electron with this silicon atom. But since it is having only 3 valence electrons, it doesn't have anything to share with this silicon atom. Okay, so it cannot share anything with the silicon atom, and therefore there is a hole here. Okay, and hence it is called as extrinsic semiconductor. All right, so if you add a pentavalent impurity, then you can have an excess of electron. Okay, that is a free electron is available, And when you add a trivalent, when you add a trivalent impurity, boron is a trivalent impurity. Okay, so when you add a trivalent impurity, there is an extra hole. Okay, we can say like that. There is an extra hole, and both are intrinsic, extrinsic semiconductor, and we can name that when when there is excess electron, then it is called as N-type semiconductor. When there is extra hole, then it is called as P-type semiconductor. Right. So now I think we can compare intrinsic and extrinsic semiconductor. So intrinsic semiconductor, we can say that it is a pure semiconductor material. No impurity atom is added to it. So if you use silicon atom, then you can add more silicon atoms to make it intrinsic. Okay. And when you come, okay, here, extrinsic semiconductor. So this extrinsic semiconductor is formed by doping a small quantity of impurity atom. Okay, that impurity atom can be either pentavalent or trivalent. All right. Okay, so example for the intrinsic semiconductor, crystalline forms of pure silicon and germanium. Yes, so that can be intrinsic semiconductor. So the example for extrinsic is silicon and germanium crystals with impurity atoms. So you have to add either pentavalent or trivalent. Okay, arsenic, antimony, okay, boron, phosphor, like that. And then the next point, the number of free electrons in the conduction band and the number of holes in the valence band is exactly equal. Okay, so the number of electrons in the conduction band and the number of holes in the valence band will be equal. So probably in the intrinsic semiconductor, it is not possible to have movement of free electrons or free holes. Okay, whereas in case of extrinsic semiconductor, the number of free electrons and holes is never equal. So there is an excess of free electron or an excess of holes. So because of this, there is a probability of using the free electron or hole to conduct currents. Okay, and the next point is that the electrical conductivity is low. So that is why, since it doesn't have any free electron or free hole, it is very difficult, or the conductivity is low. All right, extrinsic semiconductor, the conductivity is high because of the excess, because of the presence of excess electron or excess hole. Okay, all right, then the next one, its electrical conductivity is a function of temperature alone. Okay, so here the only possibility is that we have to increase the temperature in order to excite any electron or hole. Okay, when it comes to extrinsic semiconductor, its electrical conductivity depends upon the temperature as well as on the quantity of impurity atom. Okay, so it also depends upon the temperature, but also uh, the quantity of impurity atom is also a factor. All right, current in semiconductor. So the current in semiconductor can be either due to the flow of electrons or due to the flow of protons, or here we are saying is as a whole. Okay, we can say that the current due to electrons or the current due to holes. All right, but whereas in conductors the current is only due to the flow of electrons, and in conductors there is no hole movement, but in case of semiconductor the holes is also playing a role in current, right? Okay, the electrons of an atom can exist only within prescribed energy band. That one we have already seen, that the electrons exist only in at a prescribed band. Okay, prescribed energy band, that is the electrons prescribed energy band means it is nothing but the shell, right? So prescribed energy band is nothing but shell. So the electrons are present in the shell, right? Okay, so each shell around the nucleus correspond to certain energy band and is separated from adjacent cell by band gap. So that means, so this is nucleus and this is shell number 1, and there are some electrons at this shell and it is separated by a band gap, and the next shell is also separated by a band gap. Okay, so if a electron want to move from shell 1 to shell 2, then it should get some energy and it should jump from shell 1 to shell 2. It cannot exist in the band gap. Okay, so electrons always exist in shell. Okay, that is the prescribed energy band. All right. Okay, then the next point, an extrinsic silicon crystal at room temperature has sufficient heat energy for some valence electrons to jump the gap from the valence band to the conduction band, becoming free electrons. Yes, so this the statement is saying that, so you see, at room temperature, okay, there is some sufficient energy in which the valence electrons, if there is a valence electron, the temperature excite this electron and it becomes free. Okay, that means the electron gains some energy from the room temperature and it comes out of this atom. Okay, and it will be a free electron. Okay, and then when an electron jumps to the conduction band, a vacancy is left in the valence band within the crystal. This is called hole. All right, so what happens here, there is an electron here and that electron gains some energy from the room temperature and it comes out and it becomes a free electron. Okay, it becomes a free electron. And what happens to this place? So now it becomes a hole. Okay, because this the electron comes out and this becomes a hole, and that is why it is saying that there is a vacancy and that vacancy is called as hole. All right, so now we can say that, you see the same picture, you see the same picture is here. So at room temperature an electron gains the temperature and it comes out, and that electron will become a free electron, and then it began the place where it was originally placed. Okay, that becomes a hole. So that is why we are saying that for every electron raised to the conduction band. Okay, so this is a process. What is the process? At room temperature the electrons gain some energy and it comes out. So when it comes out, there is a free electron and there is a hole. Okay, so this is the process. So at the end of this process, we can have electron hole pair. Okay, so there is one free electron and there is one hole. So that is why we are saying that for every electron raised to the conduction band, there is one electron hole pair. Okay, all right. So then the next term is the recombination. Okay, sometimes recombination occurs. Okay, why? Because sometimes this energy will not be sufficient to excite this free electron, okay, to come out and to occupy the next conduction band. Okay, for example, you can see here, this is valence band. Okay, so this is valence band and it will get some energy, and that energy, with the help of that energy, the electron comes out. Okay, and it may not reach the conduction band, it may fall down, back. Okay, or you see the electrons in the conduction band, okay, lose energy and falls back to the valence band, and this is called as recombination. Okay, you see recombination occurs when a conduction band electron loses energy and falls back into a hole in the valence electron. Okay, in the valence band. Sorry, in the valence band. Okay, so that is called as recombination. All right. So now we can say that there are now we can state the two current. One is the electron current and another one is the hole current. So first, let's state the electron current. When a voltage is applied, okay. So here, voltage means is an external force. Okay, instead of heat energy, now we are applying voltage. So when a voltage is applied across a piece of intrinsic silicon, the thermally generated free electron in the conduction band, which are free to move randomly in the crystal structure, are now easily attracted towards the positive end. Okay, so positive end means what? It is attracted towards the hole. Okay, so normally the electrons are attracted towards the hole. Okay, so electrons are attracted towards the hole. And this movement of free electrons in a semiconductor material is called electron current. So we can say that the electrons move towards the positive holes. Okay, we can state like that. Holes are positive ions. All right, positive holes. So the whole current, you see, when an electron moves from one place to another place, okay, then that means it also leaves a hole. Okay, so that indicates that the hole has moved from one place to another place, and when there is a hole movement, it can also cause current. Okay, so although the current in the valence band is produced by valence electron, it is called as hole current to distinguish it from electron current in the conduction band. Okay, so here we can say that the hole current is also existing in the conduction band. Okay, so here you can see the hole current. You see, normally this is the first instant. A free electron leaves hole in valence shell. So you see, a free electron leaves the valence shell and obviously it reaches the conduction band. Okay, so when it leaves like this, there is a hole. So a valence electron moves into first hole and leaves the second hole. So here, this is a valence band. Okay, so the electron moves from here to here and it leaves a hole here, and subsequently you see a valence electron moves into second hole and leaves a third hole. So you see the electron moves here and here it becomes a hole. Okay, and similarly the fourth one, a valence electron moves into the third hole leaving a fourth hole. Okay, and here the valence electron moves into the fourth hole and leaves a fifth hole, and subsequently a valence electron moves into a fifth hole and a sixth moves into the fifth hole and leaves a sixth hole. Similarly, it leaves seventh hole, eighth hole, ninth hole. So that means one side you can see the movement of electrons, but similarly you can also note down the movement of holes. So you see, this is the hole movement. Okay, so you can see the hole movement in the valence band, and this is called hole current. Right, n-type and n-type and p-type semiconductor. All right, so we know that intrinsic semiconductor does not conduct current very well. All right, because of the limited number of free electrons. We know that in intrinsic semiconductor the number of electrons and the number of holes are equal, so it is very difficult to get free electrons or free holes. Okay, um, that is why the conductivity is little bit lower compared to extrinsic semiconductor. So this intrinsic silicon must be modified. So we have to modify this intrinsic silicon or germanium to increase the conductivity. Okay, that one is done by increasing the number of free electrons or holes. So we are going to add some impurities to this intrinsic material. So when you add some impurities, this intrinsic material will become extrinsic. Okay, so that extrinsic is divided into two types. One is N type and another one is P type. Okay, and this N type and P type semiconductors are the key building blocks for most type of electronic devices. Okay, all right. So P-type semiconductor. So when a trivalent impurity is added to an intrinsic or pure semiconductor, then it is called as P-type semiconductor. So the trivalent impurity. Why we are adding trivalent impurity? Trivalent impurity is having three valence electrons, whereas silicon and germanium, they are having four valence electrons. So when you combine this, okay, when you combine these, then there may be a hole. Okay, as we discussed earlier, there may be an excess hole, and the excess hole is what? Positively charged. We can say that it is positively charged and it is p-type. Therefore, it is called as p-type semiconductor. So the trivalent impurity is called as acceptor atom. Why it is called as acceptor atom? If there is a hole, it can accept electrons. Hence, it is called as acceptor atom, because it can accept or take up one or more electrons from the crystal and become a negatively charged particle. So in p-type semiconductor, the number of holes is more than the number of electrons. So holes are measured as majority charge carriers. So in case of p-type semiconductor, the holes are the majority charge carriers, and the electrons are referred as the minority charge carriers. So because we don't have the electrons, it is an acceptor, therefore the electrons can come and occupy this place. So since we have an excess hole, it is called as holes are the majority charge carriers, and we don't have excess electron, therefore electrons are the minority charge carriers. N-type semiconductor. When a pentavalent impurity is added to the intrinsic or pure semiconductor, then it is called as N-type semiconductor. So pentavalent impurity means it is having 5 valence electrons. So pentavalent means 5 valence electrons, whereas silicon and germanium are having 4 valence electrons. So there will be an excess of 1 electron. So when the electrons are more, then it is called as N-type semiconductor, right? So you can see that the pentavalent impurity is called as donor atom, because it can donate an electron to the neighboring atom. Okay, so that means it is ready to give a free electron to a semiconductor. Okay, so the purpose of doing this to make more charge carriers or electron wires available in the material for conduction. So that is the purpose of combining the pentavalent impurity. If you add a pentavalent impurity, then you see the number of electrons will be more, and possibly it can conduct very well. All right. So in N-type semiconductor, the number of protons is more than the holes. So electrons are measured as majority charge carriers. So since electrons are more, it is called as majority charge carriers, and the holes are referred as the minority charge carriers, because they are not. So there are two pictures, and among the two pictures, one is N-type semiconductor, and another one is P-type semiconductor. All right. So which one is N-type semiconductor? Is obviously the first picture, okay, because it is having an excess electron. So excess electron means what? If it is excess electrons, the electrons are more. Okay, therefore it is called as N-type semiconductor, and we can easily say that since the electrons are more, electrons are the majority charge carriers, and hence it is N-type semiconductor. When you come to the second picture, you can see the hole. Okay, there is an excess hole. Okay, when there is excess hole means what? The holes are majority charge carriers. If the holes are majority charge carriers, then it is called p-type semiconductor. Okay, let's review atoms, molecules, protons, electrons, and neutrons.
Hello,
What
friends.
we have
I
discussed
am an
so far.
atom. Yes, an atom. Can you see me? Oh, yes, I know you can see me on your screen, but I am just an imaginary picture of an atom. Real atoms are too tiny. You can only see them under a very special microscope. Actually, this big microscope can be called a machine. Okay, now you know that we're so tiny that we can only be seen with machines. Now I have a question for you. Do you know the meaning of your name? Very good if you know it. If you don't know, ask your parents. But I also know the meaning of my name. It means that which can't be cut, that which is uncuttable. Actually, it's a Greek word, which means it is indivisible, which means it can't be divided further or can't be cut further. Let me show you something. Let me ask this man to cut the apple in his hand in half. Now do it again. Please do it again. Keep doing it until you can't cut it any further. Yes, this is the smallest part which you can't cut any further. But it can also be cut under a microscopic machine. So, if you get a part so small which can't be divided further, it is called indivisible. It can't be cut further. It is uncuttable. It is an atom. Let me tell you a secret. Everything is made up of atoms. You, this water, this table, this blackboard, this fan, these fruits, everything. Everything is made up of atoms. Oh, you're right too. Everything is made of molecules, but all molecules are made of atoms. Confused? Go to the blackboard and write any sentence. Good. Now this is a whole sentence. Now circle all of the words in this sentence. Now let's take a word and circle all the letters of R with some other color. Very good. You see, this sentence is made up of words, but words are made up of letters. So letters are the smallest units of a sentence. Similarly, everything is made up of molecules, but molecules are made up of atoms. So atoms are the smallest unit of everything. Look at this. See, water is made up of water molecules, but water is made of atoms. There are 2 atoms of hydrogen and 1 atom of oxygen in each water molecule. So when atoms join together, they form a molecule. And when molecules join together, they form a thing. So now you understand. Good. So now, friends, now I would show my body. Yes, I would show different parts of my body. In the center of an atom, there is the nucleus. It is made up of even smaller parts. These are called protons and neutrons. Each of these protons carries a positive electrical charge. The neutrons are equally as heavy as protons, but don't carry any electrical charge. So, the nucleus of an atom is positively charged due to protons. Now, electrons are outside the nucleus. They are orbiting around the nucleus. The electrons carry a negative charge. The total negative charge of electrons is equal to the positive charge of the nucleus. So in total, an atom is neutral. The positive charge of the protons is neutralized by the negative charge of the electrons. So it is like +1 is neutralized by -1, and overall charge of an atom becomes 0. The electrons are moving outside the nucleus at a very high speed. Can they run away from the nucleus? No, they can't run away. Every atom has the same number of protons, electrons, and neutrons. So there is an attraction between equally strong negative and positive charges. Due to this attraction, electrons can't run away, as positively charged protons keep them pulled towards them. Hope this is all clear to all of you. Otherwise, you can always go back and see it again. Now let me explain how we atoms bond together to form a molecule. It's just like the letters getting together to form a word. Electrons keep moving in shells outside the nucleus. Each shell contains a fixed number of electrons. The first shell can have 2 electrons, and the second can have 8 electrons. The third can hold 18, and the fourth can hold up to 32 electrons. The atoms in the outermost shell of an atom are called valence electrons, and the outermost shell is called the valence shell. Atoms bond with other atoms to form a molecule with these valence electrons in the valence shell. Remember one thing, atoms always keep trying to fill their shells. Take, for example, an oxygen atom. In its second shell, it can hold up to 8 electrons, but the oxygen atom only has 6 electrons in its second shell, so it is always looking for more electrons to fill its shell. Now, here is a hydrogen atom. It only has 1 electron in its outer shell, but it can hold 2 electrons in its shell. So it is also looking for more electrons. So the oxygen atom bonds with 2 hydrogen atoms to fill its valence shell by sharing 1 electron from each hydrogen atom. In this way, the hydrogen atom's requirement is also fulfilled, as they can also fill their shells to their capacity of 2 electrons in their valence shells. By combining together, they become water molecules. So friends, now you understand us. I am part of you. So learn us well by watching this video again and again.
Thank you.